Next, I have Mr. Joseph Whiting, if he is here, I believe. Joseph, is that you, sir? Yeah, let me see. Oh, I cannot hear you though. And so let me do this. There we go. Let me do it. Let me do a brief introduction. So Joseph Whiting, he actually mentioned this during the last conference, and I took good notes and followed up with him. So I did my job. He's going to do an introduction to a novel apparatus for investigating the properties of vortex ring cavitation in relation to sonoluminescence, superfluids, Bose-Einstein condensates, solitons, and the Casimir effect. The apparatus is highly customizable and allows for a wide spectrum of test materials. And Joseph, thank you, sir. He was really flexible too. He emailed me at the end of the last conference, and I was like, "This is awesome! Come on!" So well, thank you, sir.
Thanks for having me on. It's an honor.
Yeah.
So first off, I put a link in the chat for everyone. That's the entire body of research for everyone to take a look at later.
Now, do you have a PowerPoint that you want to bring up, or?
I do. Yeah, I do. I'm going to share the screen here.
Okay, and what I'll do is spotlight you, and yep, and I can see your super widescreen awesome monitor.
Cool.
Whoa.
All right, so the presentation today is vortex ring cavitation, and it's kind of like I want to open up kind of a new area of research, something that might fit into these things that we're observing. And so first off, I just want to like take a look at bubble rings. It's not something that we think about very often or see very often. So here's a short video from Caltech. Can you guys see that?
Yeah.
Okay. And hear it?
Well, yeah, and actually it's better without the audio, because that when we have video and audio, it gets us into trouble with copyright.
No worries. Oh, okay. Yeah, got you. So yeah, just pointing out here, like, you know, they're really stable objects. They just have some weird properties. It's kind of a, you know, more of a visual thing. You can just kind of see it, but you know, I kind of look at them as almost like a macro soliton. Essentially, it's like well, yeah, just they really do speak for themselves. And yeah, so I just wanted to kind of take a look at that. And they go on to say how they figured out a nice model for it. And then this is just kind of a fun video of these dolphins messing around. So yeah, we kind of get the idea. And then yeah, this was another interesting video. This guy, he kind of so this is like a mixture of gas and it's a mixture of propane and oxygen. And we get some nice high-speed footage. He's gonna detonate these rings, and it's just wild, like how detonations can occur in them, and you know they just seem like such a robust structure, and we know these structures exist all over the place in nature. You know, that's essentially like what the convection cells look like that form the vortexes we see. Yeah. So then I ran across this really interesting video, and this guy's highlighting the difference between the behavior of the bubbles depending on if they're like under a vacuum or not, you know, like, because one's going to be mostly, we do have to hear, there shouldn't be anything copyrighted in this one. So here we go. Let's go here. I'll just play it from here. Can you guys hear it? No? Okay. So it's essentially when he uses these for other projects, and when he's done, he gets this sealed container, and I wish you could hear it, but it's like, it sounds like there's a BB in there and it's like tinging around. So in like one case, you've got, this is like when it's open to air, you can see the top is broken and it's open to air. So that's got the gas in there. So it, you know, it's not going anywhere. But in the last example, this one, there's a vacuum on the chamber. So these bubbles are actually just, it's a vapor of the fluid, but it makes this crazy sound. And then we get to see that in high speed. And these are with what I'm calling the vacuum bubbles. Okay. So I thought that was interesting because, you know, there's pressure waves bouncing off the walls of that container that's, you know, ultimately determining that weird nucleation when the vapor, because it's like a vapor will get compressed elsewhere as he's swinging it, and then all of a sudden you'll get these nucleations of vapor that just appear. And that just, you know, I think that ties into what is going to go on here. So the next thing is sonoluminescence, and the mechanism of sonoluminescence is completely unknown at this point. There, you know, the whole kitchen sink's been thrown at it, really. You'll see a folder in that link that has a lot of research that's been done. It was first observed in the 30s, I believe, and you know, it was a hot topic in the 90s because they were thinking maybe some sort of fusion was happening, but I don't think any of that work panned out. I think they were able to test that out. But, you know, as you can see, the hypothesis include, you know, thermal plasma, phase transition radiation, condensed states of matter. I mean, you know, the entire kitchen sink, really. But there's some weird things about it. You know, the bubble collapse is incredibly fast, and you know, the so fast that it's said to be adiabatic, meaning that like there's no energy transfer. So if there's a gas in there and the bubble gets smaller, it heats up, and then the bubble gets bigger, it cools down. And they've read, you know, everything from negative 269 Kelvin to like 10,000 Kelvin, in some cases as high as 20,000 Kelvin. It really is a pretty incredible phenomenon. But once again, it is kind of one of those visual things. So there's a video here. We kind of get to see like the basic setup, and so what he has going on here is Pretty much something like this. The basic setup is out there. You can find many sources on the basic setup for sonoluminescence, but it essentially consists of a spherical borosilicate flask, and then these are two piezoelectric transducers, and those are going to be your drivers. This one down here is just a microphone, so we can get a readout on it, and the whole goal is to have your drivers be outputting the resonant frequency of the whole container. So then you get these nice like spherical compression waves coming off the entire container and coming to the center. And that's when you introduce your air bubble, and you'll find it won't float to the top. It'll just stay there. And when you fine tune it, you can get it to the point where you're getting one flash of light each acoustic cycle. So if you're running it at 20 kilohertz, then you're getting 20,000 flashes a second. And the light temperature they're reading off these bubbles is like astronomical. But then other theories are saying how, well, you know, the expansion phase implies some sort of ridiculous cooling amount. So you kind of have like two ends of this where, you know, a lot of folks are in the thermal radiation boat, and then some other folks are in the cold matter boat. But then there's kind of this third one that's emerging more recently where they, you know, they think it might be more of a quantum phenomenon, and that has to do with the dynamical Casimir, and what's it called? The dynamical vacuum effect, I believe, or dynamical Casimir effect is one of those two. But here's, yeah, this video. No sound. Okay. So we'll kind of get to, you know, just kind of see it. It's always fun. And so what's interesting to note is that the two bodies of research where they differ is that one is assuming that the flash of light is correlated with the bubble minimum radius, you know, max compression. But, you know, other types of analyzing, so most of your thermal radiation people, they're using red lasers, and then the people that, you know, essentially someone set up a Schliering imaging instead of a red laser, so they could focus incandescent light onto the bubble to get like a broader spectrum on the analysis, and it comes over as like a higher resolution. And they found the flash to occur like way before the bubble minimum radius, which implies that, you know, there was some sort of phase change during the expansion phase of the bubble. And then when that bubble starts collapsing back again and reaches an unfavorable state for the type of matter that was created, it'll change back. I mean, the most simplest way of looking at that is that the gas like freezes so fast that the leftover energy of its motion gets turned into light once it comes back into a fluid. But yeah, that one shot where he's like moving the bubble around, he's like changing the dial on the oscilloscope, right? And so it just requires some fine tuning to get these things to the point where they look like stars in jars. And what's that one? So you know, and so I guess what I'm doing is I'm saying, okay, like, why not do this but to a bubble ring, right? Like, can we cavitate an entire vortex ring? And would that give us better clues as to what is actually occurring in this phenomenon? Here's some experimental observations from various research. And yeah, so the expansion class is adiabatic. Larger bubbles, lower frequencies, cooler ambient temperatures, and higher static pressures will have brighter, more energetic discharges. The bubble emits a single bright flash once per acoustic cycle. Typical drive frequencies are audio to ultrasound, but it's also seen in subsonic and megahertz band. During the expansion phase, the bubble expands to a volume that is more than 100 times greater than the initial equilibrium volume. The bubble collapses and bounces several times, about 50 to 100 nanoseconds before the first minimum. Oh yeah, that actually brings up a good point. I should show you like the chart. So this is like your typical chart for this. You'll find this in most research. Most research uses this equation to do their analysis. And this is where like the quantum group says, hey, you know, this equation isn't up to it because when you use this equation, it implies that there's a faster than light speed on the bubble wall as it approaches this minimum. It's kind of like the same problem you run into with GR and quantum mechanics. It's like the singularity, like something's going on there. So that's where initially, like in the 50s and 60s, they were using red lasers, and they were just kind of assuming that this compression ionization effect was occurring. But yeah, so the flash of light happens only on the first bounce, and then there's these subsequent smaller bounces, and then it'll go straight into the next expansion phase. And if we want to like zoom in or get a better idea or display the non-linearity of this, this noise, this perturbation in the fluid, then this is a really good chart for that. You can literally like see the non-linearity in it, which is great. And it's just because it's a resonant structure. So you're going to have all these subharmonics that, are involved. So it's this really strange effect. And it merits more attention than it gets, and I think it might be relative to the kind of technology that we're seeing in these crafts, because oh yeah, let's keep it here. So yeah, so that's what's really cool. Yeah, variety of liquids and gases. Like you can do water and air, you can do water and helium, any of your noble gases. You can use more or less viscous fluids, sulfuric acid, or something that's more, something that's less viscous. And that changes a lot of things. You'll have brighter bubbles with heavier gases. There's charts that show, same fluid but different gases. And of course, like xenon has the brightest measurement. And in this video here, what they have is they have a test tube that is sealed, and there's a slight vacuum in there. They've got xenon gas, and can't remember what the fluid was. But it's important to note that in this case, what we're seeing here is something similar to that video of the guy who had the water, that nucleation that we saw. So I'll show the Putterman ones in my files here. And they're not using ultrasound to get this one. They're just using the flick of a wrist. And this is a great video. If anyone's interested in this topic, this is like a great primer. It's about 2 hours long. But Yeah. So, you know, that's a lot. That's high energy for, you know, just someone shaking a test tube. You know, those little flashes of light are incredibly bright. And you know, there's a difference between obviously having a bubble that has a slight vacuum or has a vapor in it to like having it at a gas with pressure, because you know it's been seen that higher static pressures have more energetic discharges. So you know, there's a lot of data out there on this, but there's really no conclusions. So some speculations utilizing research that is available is that a bubble at room temperature with an equilibrium radius at 8.5 micrometers will expand your radius to 63.8, giving you a temperature drop to about 5.8 or 5.3 Kelvin. And so, and then also, you know, the brightness, it's about 7 mega electron volts, which isn't really a lot, but that's a lot for, you know, the atomic scale. You know, if this could be pushed higher, you know, you could have maybe fusion or things, but so, you know, the question is the temperature drop turning the gases into superfluids or condensates, or is this like, I mean, you know, I guess my favorite way of putting it was from this paper, and he, you know, he says that pondering this, one has to admit that all we really know is that photons come from some kind of moving charge or field, theoretically speaking, from the coupling to a fermion field. So, you know, something's going on here. So it's either going to be more of that traditional route, fermionic field, or we're going to have some weird, you know, more quantum, maybe a superfluid kind of thing. So just more investigators is needed. But I want to skip bubbles and just kind of throw this into a closed loop system. And there have been some of those papers, you know, they get crazy on the light temperature. It's hard to tell in today's world the accuracy on most things, but I mean, I think the highest one I read was 188,000 kelvins. They were using like mercury or something. Yeah. Oh yeah, so then, you know, the people in the quantum domain, you know, they're saying that, you know, these could be, you know, more like coherent structures and more related to the vacuum. So, you know, I guess that kind of rolls into the concept, and the 3D models, those are just probably not how it would actually look, but just as a good visual, they are there. But I want to create a device that can produce a stable bubble ring inside of a torus-shaped container, and then cavitate that bubble using sound waves. And then explore that, but with different materials, different phases, pressures, combinations. And I want to do both, you know, use gases at various pressures, but I also want to see, you know, about vacuum bubbles. That's really caught my attention, is that when you have, you know, obviously when you pull the vacuum, you're going to get a vapor of the fluid, but, you know, it's still pulling a vacuum. So when that bubble expands, you know, like it's pulling even more vacuum. And if it's expanding so quickly, you know, if the process is adiabatic, then how does more of the fluid turn into a gas as it expands? So it would, you know, be pulling an additional vacuum. So maybe that does bring in kind of, you know, vacuum induction, because if normal induction is just a coil with an electric charge moving through it, and we can transfer power, move a magnet, or do work with that, then if we want to mess with the vacuum or space-time or whatever we'd like to call it, you know, don't we want a coil that is kind of like a piece of vacuum, but we're doing stuff to it? And I figure sound would be perfect for that. And I'll bring up some interesting points, some new research about, you know, about sound and how, yeah, I'll get into that. I got to slow down. I'm really excited to be here with you guys. All right. So yeah, this is just a brief description of the device. A borosilicate glass toroidal chamber with barbed hose fittings to allow the additions of liquid gases and to control the level of pressure or vacuum. Copper coils, or preferably some high temperature superconducting ribbon would be nice to use here. Are wrapped around the chamber. Ultrasonic transducers are epoxied to the glass torus. And this is funny, you mentioned that cryogenic epoxy set you back a lot. And that's funny because I do want to submerge, you know, depending on what fluids and gases you're using and what path or theory you're kind of testing with this device determines on whether you're going to submerge it in some sort of warm fluid or a cryogenic fluid. So so you've got your coils, you've got your transducers. Now, ideally, you'd only need one transducer, which would be really nice. I just kind of made it look cool, but really, preferably, if you get away with one transducer, and you know the coils are there, so you get an idea what it looks like. And we're essentially doing sonoluminescence, but in a donut shape. So here's kind of 3 example experiments, and I brainstormed a lot of different materials and phases and things, but here's like 3 that I really like. So in the first example, let's say we chose liquid oxygen as the magnetic fluid, and helium-4 as the gas. And so, you know, in this case, we are asking, you know, is it a cold condensate situation? And so what we would do is we would use the electromagnetic coils to, you know, move the liquid oxygen around the container. And, you know, right there is like a first issue is, you know, turbulence in a closed system like that is a problem. But, you know, cross those bridges when we get there. And you could have computer control on the coils and a device that can read that and maybe even teach a neural net to get the flow as smooth as possible. But let's say you get a nice flow of helium, of oxygen, so magnetic liquid oxygen, and we filled that tube up most of the way, but we left a little bit on top to fill in with helium, and let's say we take it to 1 atmosphere. So hopefully when we get this liquid oxygen spinning around the tube, we'll get a bubble ring in the middle there, because all of the gas should move to the lowest pressure point of the system, which should be the center area. And so if we can get a bubble ring and it's nice and stable, then we could turn on our sound, turn on our transducers and see if we can't cavitate that. And I bet you there'd be some really cool things as you fine tune it, like where the ring is like separated into separate little bits, but it's still kind of coherent because of the way, you know, they're such stable structures. And so then we would see, you know, one thing that's cool is like, you know, sonoluminescence, no one can explain it fully. And then also no one's really put it into a ring format like this. And there's some, there is a really good video. Actually, it's right. Oh yeah. So in example 2, it's like the same setup, use liquid oxygen as the magnetic fluid component, but try to omit gas. So like, you know, pull a vacuum over that. We might get some liquid oxygen vapor, but if the whole apparatus is submerged in liquid nitrogen, then that liquid oxygen won't be able, you know, it won't be able to warm up, which will be nice. And you know, if we can get away with pulling as much vacuum as possible without getting too much oxygen vapor in there, so that when we're actually cavitating the entire vortex, like if there really is an expansion phase of 100% on the full vortex ring, then I mean, that's like when you bring that spherical research into the domain of like a full-blown torus, like your surface area, your volume, everything is just like increasing a lot. So if they're getting energy contents of, you know, 7 mega electron volts from a tiny bubble, then, you know, what can you do with a ring? And then on top of that, if it is like, if it is a fermionic thing, then can you couple to it? You know, if it is a weird instance occurring in this phenomenon, then since we have it in a container surrounded by electromagnets, can we, you know, take it further? And then in another one, this would take a lot of design changes and would be really expensive, but you know, liquid helium-3 is can be worked upon by the electromagnetic coils and can be accelerated. And then you'd have like, if you were doing the vacuum bubble version of this, it would be like liquid helium-3 and then helium-3 vapor in the ring that you'd be cavitating. You could maybe mix in other isotopes. You know, this would be more like can you kick off fusion with it? So there's just a lot of really cool things in this field. Just so some questions is, you know, can further tuning be used to couple the phenomenon to the magnetic field of the driving coils? Can this coupling be used to fine-tune, control, or interact with the phenomenon? I pretty much covered all this. Yeah, can deep neural net achieve laminar flow in a closed system? Can a deep neural net be trained how to play the ring like an instrument to find and maintain the desired optimal conditions? Can the torus-shaped bubble be tuned to hold the helium-4 bubble or the vacuum bubble in a special state? Does this state share any properties with superfluids or other macro quantum phenomenon? Or perhaps like, you know, vacuum stuff, Casimir stuff. Some references, you'll find all these on the paper and a lot of it's in the body of research. But just some weird highlights from the research. Oh, I crammed it all in this 20 minutes. Oh, I'm so bad. Okay, we'll do a long Q&A, so you guys can. Okay. So this is from reference 16. This is what's his name? I forget it, but an ultra-cold gas of bosonic atoms at sufficiently low temperature undergoes a phase transition known as a Bose-Einstein condensation and becomes essentially a macroscopic quantum system. It is macroscopic both in the sense that on the order of 1 million atoms may be occupying the same quantum state, and in the sense that this system can be hundreds of micrometers or larger in size, large enough to be resolved even with the naked eye. Such a gas is superfluid, and when confined in a ring-shaped trap, can support a persistent current, a superflow that is undamped for as long as the gas itself can last in an imperfect vacuum. This flow is on the basis for an atomtronic closed circuit where the flow of atoms is analogous to the flow of electrons in electronic circuits. The unique opportunities for control and observation offered by atomic gases, along with fluid versions of Josephson junctions, have produced a wealth of interesting results. So, you know, if there are results, you know, one of them could be that, you know, you can stabilize one of these, but maybe with like an 8-inch radius or something, you know, inside this thing. And then, you know, is that how we get to the cool propulsion technology that we're seeing. So yeah, the sound, this is, and check this out in the references. It's a really good paper. And these guys are saying that they've got a new calculation that indicates for ordinary sound waves in most materials that the mass carried is equal to the sound wave energy multiplied by a factor that depends on the speed of sound in that medium's mass density. And that brings us into questions like, you know, what is the speed of sound in a superfluid, or what is the, you know, speed of sound in a quantum object? And the mass carried by sound waves turns out to be negative. It's a depletion of mass rather than an addition of mass. So sound waves in a gravitational field should float upwards somewhat, like any buoyant object in water. For a 1 second long 1 watt sound wave in water, the amount of mass would be about 0.1 milligrams. It's honest to God gravitational mass, the one we experience every day. Says one of the team leaders. It's a simple fraction of the total mass of the system that travels with the wave being displaced from one place to another. So this would be like an interesting thing. So if you were to omit gas and just have a, you know, vacuum bubble in this device, you know, if sound is carrying, you know, a fraction of the total mass of the system, well, if part of that system is this like vacuum object, like literally, you know, a ring of vacuum with like a fluid walls, and you're like doing stuff to it, if we found out how to do stuff to it right in the right way, then could we resonate that ring with essentially the vacuum? Like, can you resonate, kind of like with induction, can you resonate this small vacuum bubble with the vacuum at large? And then if so, is the sound wave that's traveling through that, is the sound wave going to carry a fraction of the total mass of the system? Because a fraction of the total mass, you know, of the entire vacuum would probably be enough juice to get you to some point where you can figure out how to actually engineer space-time to fly somewhere. And then kind of from you know, a quantum perspective, and this reference comes from some Hal Puthoff stuff, one of his papers, and he states that the vacuum energy can contribute both positive and negative energy to the vacuum, and that you've got virtual fermionic fields contribute overall positive energy to the vacuum, whereas virtual bosonic fields contribute an overall negative energy to the vacuum. So, I mean, there could be the case where you're getting both in one. Maybe the expansion phase is, you know, giving you some sort of coherent, you know, it also depends what material you're using, right? Whether it's a boson or a fermion, but, you know, it could be that something's happening at the expansion phase and there's another something happening in the compression phase. But, you know, we get to change, we're like changing the conditions on this bubble so quickly and so violently. You know, if that was just a piece of vacuum, could you resonate it with the rest of the vacuum? And so they talk about in the full paper, Puthoff discusses coupling to these virtual fermionic fields. If you're in the framework where you allow one extra dimension to, you know, to have a compactified extra dimensions where fermionic fields go into, or they're virtually there, then they were saying you could potentially couple to the fields in those dimensions and then gain influence over the local expansion rate of space-time. So it would essentially like give you control over dark energy, or, you know, stuff like that. But the paper's 30 pages long. Like, I cherry picked a lot of the good information from probably hundreds of papers regarding the topic of sonoluminescence and you know, vacuum engineering and all this stuff. And I've just noticed these really strong correlations with what we're seeing from real world, you know, real world data from the videos and things. And then kind of what we're seeing with, you know, sound is a big part of it. And if sound is really kind of a manifestation of mass in this, you know, weird way of looking at it, I mean, you know, that's its like sound is gravity's analogy already. Like gravity is just like sound waves in space, right? They're waves of the medium that is space-time. So you know, I just think there's a strong correlation, and unfortunately, you know, I don't know like what's going to happen. I'm just kind of here to say, here's a brand new phenomenon that you know is not getting attention in this field, and I think this is the I think this is like really key in some ways. So that was the whole PowerPoint. I'll keep it up. Those graphs were great. I'm gonna go. So NASA, you know, they took their shot at this too, and they actually produced some really nice imagery. This is a really cool one, so you can actually see these luminescing bubbles, and they're already forming this ring-like structure. You can kind of see it, and so, and this is a minute-long exposure, so you can kind of see the dance. So this is multi-bubble sonoluminescence. So you can see there's these luminescing bubbles all over the place. That's at 108 kilohertz, 100 milliliter beaker. Really, really pretty. And then these are some cool ones. Once again, it kind of has this ring-like thing going on here. You know, I don't think it'll be hard to coax it into a ring. I kind of think. And I mean, there's just so much questions to be answered here. Like, is the collapse perfectly symmetrical? Is it an asymmetrical collapse? You know, what, you know, people were trying to detect neutrons out of it. That's when they thought they had fusion, but later it was ruled out there really are no neutrons in there. But then some other people are like, well, look, these energy levels that we're reading could initiate that. But I really, what I put my money on, what I'm most interested in to see is the vacuum bubbles and what sound does to the vacuum. Let's see. I know they got some cool pictures of single bubble in here, I'm pretty sure. Oh, here's a cool table of some different solvents used. 80% glycerin, that one's probably so thick. But I mean, you know, you could use metals, you use all sorts of different things. You know, any magnetic fluid you can put in to this device. Any gas, or just leave the gas out. There was one more. Yeah, here's some cooler pictures. I think this is just the same body of, yeah, same body of research. Yeah, so I mean, that's really the summation of my idea. Sorry, I just kind of crammed that out there so fast. Here we can see a nice shot. It does kind of have this vortex-like thing going on here. So, but yeah, 1934. And this stuff's just been pushed under the rug for a long time. But I think there's some really good stuff to be had here. So
awesome. So Joseph, is that pretty much it then for your presentation, or?
yeah, I rushed through that. I probably should have slowed down, but I
Oh
just
no,
once I
that's
get
cool,
going,
man. That's
yeah.
cool.
I
Well,
figured we could have more of a question and answering because that'll help. You know, that's just a little better.
yeah. Well, so let me do this. Let me stop. I'm going to stop your screen sharing then. And let me see, I'll remove spotlight. So the very first thing I want to do is I want to put this on gallery view. Everybody, please put your hands together. Give Mr. Joseph Whiting a giant applause.
Thanks, guys.
Again, it feels like we're back. We're doing in-depth work. You know, Joseph, that was really deep work on sonoluminescence. So thank you, sir. Thank you.
Yeah, you're welcome.